Hi folks, let's talk about catalysts. Now, a catalyst is something that speeds up a chemical reaction. Some chemical reactions have crazy high activation energy, so high that these reactions occur very, very slowly or almost not at all due to the high energy requirements involved. And what a catalyst is going to do is speed up that reaction. The definition of a catalyst is it's a substance that will speed up a chemical reaction by lowering the activation energy of the reaction, and it does not get used up in that reaction. So let's take a look at the decomposition of hydrogen peroxide. When you use hydrogen peroxide and you pour it on a wound, it is going to decompose into water and oxygen. And in a wound, actually, it's the enzymes in blood that act as the catalyst. In a laboratory, we can use manganese oxide as a catalyst. And here's how it works. If I have hydrogen peroxide, here's my reactants, here's my products. And it has a relatively high activation energy hill it has to crawl over in order to get that hydrogen peroxide to naturally decompose. But if I add in the laboratory manganese oxide, that activation energy hill is so shallow that just room temperature chemicals react spontaneously. Here's a photograph of hydrogen peroxide. Pour in a little manganese oxide, and it is a black powder, and you get a very quick decomposition. Now, what you see in this photograph is bubbles. Those bubbles are oxygen gas. And that oxygen gas is being released very, very quickly. Why does it look black? Well, that is the black powder that is manganese oxide. So multiple things can be used as a catalyst, even for the decomposition of hydrogen peroxide. Blood can be used, or actually the enzymes in blood. Manganese oxide and light also helps catalyze this decomposition. Hydrogen peroxide is not a terribly stable compound, so there's many things that can rip it apart. There are two ways that catalysts speed up chemical reactions. One is to lower that activation energy hill. The other one is to provide a site or place for chemical reactions to occur. So if a catalyst is going to lower the activation energy, what it commonly does is provide a different chemical pathway. If two molecules are going to react, sometimes that head-on collision of those two molecules just is so incredibly inconvenient for one method or one reason or another, due to structure, due to form, due to speed, due to something, that it just doesn't work terribly well. And the catalyst is just going to provide a different way to get to the same product. And you want to get to the same chemical product. And that catalyst is going to think of it as providing an alternate route. So let's look at this analogy. Let's say you want to get to the top of a hill. And let's say you're an intrepid climber, and you are going to put on your climbing gear, use your ropes and your carabiners, and you are going to climb up the face of this mountain. Well, that is a lot of energy that's going to be required, and that is the direct approach. And I am not going to do that. I am not that sporty. I have zero experience climbing, and I'm not that strong. I'm not going to do that. But maybe there is an alternate route, and that alternate route might be using a car to drive up the backside of that hill. That's Mary's route for getting up to the top of that hill, and that's going to be that alternate path. And by using that alternate path, you can get to the same location. That's how catalysts work. Now, that alternate path might be in biochemistry very circuitous and very complicated, but it will get you there. One of the other important things about catalysts is they're not used up in the process. In the same way as I'm driving up to the top of my hill, I don't use up the road. The road remains in place. The road is still there for the next person to drive up the road. The road isn't used up. It's a pathway. And the pathway is in place and remains there for the next molecule and the next molecule and the next molecule to use. Now, catalysts in the human body, there are many of them, and they're called enzymes. Enzymes are large protein molecules, and some estimates are that there are over 1,300 of them in the human body. And if you think about the wide range of chemistry that must occur in the human body, everything from respiration to digestion to reproduction, thought, chemicals, all of the muscle contraction, we are a big ball of chemistry that is life. And also think of the restrictions. We have very precise, specific restrictions of the chemistry in the human body. It's a relatively low temperature. It's in the dark, so light cannot make these things happen quickly, and there's a very limited range of pHs, so you cannot have strong acids, cannot have strong bases, speeding up those chemical reactions. So how does life actually occur? You have to have catalysts to make these chemical reactions occur. Here is a list of some of them that you may have heard of: lactase, sucrase, maltase, pepsin. Many of these you will learn when you take anatomy and physiology, biochemistry, or organic chemistry. Another thing a catalyst does is it provides a reaction site. Sometimes reactants just have to have time and place to react. And a catalyst can actually make those chemicals sit next to each other and pushes them together to make them react. If there's not a place for that reaction to occur, sometimes the chemical reaction will not occur. So use this analogy. Let's say that these two people are looking for romance, and she's alone over here, he's alone over there, and there's no catalyst. There's no way for them to get together. So what could be a catalyst? Well, all the wonderful dating apps that are out there. That's the catalyst. It is a site for the reaction to occur. It provides something to push these two chemicals together to make the chemical reaction occur. Now, in the same way that the app does not get used up by the reaction, the catalyst does not get used up by the reaction. And catalyst will help place the right chemical with the right chemical. That's the beautiful thing about chemicals and catalysts. Another beautiful example of catalysts is your catalytic converter in your automobile. Catalytic converters reduce pollution, and they are complicated and expensive gizmos, and they're expensive because they contain some very rare transition metals: platinum, palladium, rhodium, and oxides of these metals. What's inside of your catalytic converter? A lot of surface area. Now, the gases that are coming out of the exhaust of your car are a lot of hydrocarbons, lots of nitrous oxide, lots of carbon monoxide. Those are nasty things, and we don't want them spilling into our atmosphere. And if they go through the tailpipe of your car too quickly, too fast, there's no time for them to react, and there's no time for them to become harmless. What happens in your catalytic converter? It provides a lot of surface area for those chemicals to sit down, cuddle up next to each other, and react. So the gases in a catalytic converter are not there for long, 1/10 of a second, 4/10 of a second, but it allows time for maybe 75% of the nitrous oxides to be converted into nitrogen and oxygen, gases that are harmless and already in the air. About 95% of the carbon monoxide and the hydrocarbons are converted into carbon dioxide and plain old ordinary water. All that takes is a place for the reaction to occur and a little bit of time. So this is going to reduce those nitrous oxides, those brown emissions that hang over cities, those hydrocarbon soots that are everywhere in dirty, polluted air, and carbon monoxide emissions. So to summarize, catalysts speed up reactions by lowering activation energies, providing sites for reactions. They don't get used up in the process, and the same molecules can be used over and over again. All right, folks, that will do it. See you later. Bye-bye.